Discussion we started yesterday about Ccg schemes. Let me just briefly remind you the definition. So as before, the notation is standard. So we had alpha different from 0, an element in wedge P of V tensor V, P greater than or equal to 2. Then if we apply a Koszul differential we get delta of alpha, an element here, and this can be written as a sum x capital I tensor Qi, where Qi's are quadrics, and these quadrics define an ideal whose zero set is the Ccg scheme. So SIDS, delta of alpha. So SIDS of alpha is defined by the quadrics Qi, all the quadrics Qi. And the most important remark is that there are at least P plus 1 choose 2 independent Qi's. Okay. And we have seen that in the case of 7 points in P3, if beta 2,3 was different from 0, then the Ccg variety of any non-zero class would be a twisted cubic. And this generalizes as follows. So we have the strong Castelnuovo lemma, which is due to Green, which says the following: if X is a set of D greater than or equal to n plus 3 points in Pn in general position, then Kn minus 1 of X is different from 0 if and only if X lies on a rational normal curve and why is this called strong Castelnuovo lemma? Because we have the classical Castelnuovo lemma saying that if we have at least 2n plus 3 distinct points in general position in Pn that impose 2n plus 1 conditions on quadrics, then these points must be on a rational normal curve. So it's a stronger statement than the classical Castelnuovo lemma.
General position is linearly general position?
Yes, linearly general position.
In IMAR, if degree is n plus 3, then always unique rational normal curve.
Exactly. This is that was what I was about to say. Sketch of proof. So there are two cases. First case. So if D is n plus 3, there is a unique rational normal curve C containing X. But in this case, using some vanishing results, because X will be in a rational normal curve, which is a P1. And now we can compare the Kozul cohomology of C and of X. And the surprise is that in this case one can prove, I'll just keep this proof, that Kn-1 of X is actually isomorphic to Kn-1 of C. So it's much better than the Kozul cohomology of X being bigger than the Kozul cohomology of C. And in the second case, so if D is at least 2 n plus 4, sorry, then we can pick n plus 3 points out of these. So we consider a subset of n plus 3 points, and then we have k n-1 of X will be contained in k n-1 of C of X, yes, in X prime, which is isomorphic to k n-1 of C. And this means that any syzygy of X is also a syzygy for C. And we have seen that the syzygy varieties associated to classes of a rational normal curve coincide with the rational normal curve. So any syzygy variety of an element here is the rational normal curve. So that's somehow the sketch of proof. And
the original idea is this one for green proof?
No, it's different. That's an adapted proof. The original idea is a bit longer, but okay. Why are we so interested in these Ccg schemes? Why are they interesting? Well, because these schemes tend to have small degree, and putting one variety on another variety, bigger variety of small degree, is something which is definitely very interesting from the point of view of projective geometry. And let me just introduce the following definition. So far we worked with syzygy with varieties associated to classes. But if we want to have something which is independent on the choice of a class, then we better intersect all these sub-schemes. So for P at least 2 and Kp1 of X different from 0, so as usual X is in Pn non-degenerate. We define SIDS P of X to be the intersection over all classes different from 0 of SIDS alpha. So it's the biggest subvariety or subscheme, such that any alpha is a syzygy for that projective scheme. And the first major, or probably second major theorem after Strong-Castelnuovo lemma is again due to Green, and it's called the KP1 theorem. It's the first classification result for these varieties. Suppose X is smooth of dimension M. X in Pn considered also linearly normal. Then KP1 will all be 0 for any P greater than n minus m. For instance, if X is a curve, then Kn1 of X is automatically 0. Then the next case, Kn minus m1 of X is different from 0 if and only if X is an m-fold of minimal degree. If n is 1, then Kn minus 1 is different from 0 if and only if it's a rational normal curve. And finally, the second is that Kn minus m minus 1 of X is different from 0 if and only if X is of degree lower than or equal to n plus 2 minus m. So it's either minimal degree n plus 1 minus m or 1 bigger than the minimal degree, or it lies on an m plus 1 fold of minimal degree. So for a curve, again, Kn minus 2 is different from 0 if and only if it's either degree n or n plus 1, and or it lies on a surface of minimal degree in Pn. So in other words, if we look at the tail of the minimal resolution of X, these KP1s tend to vanish unless X lies on a very special variety. That's somehow the moral of the story. Actually, what Green proves is a bit more. So these descriptions here are obtained by using syzygy varieties. So actually, in the first case, SIDS n minus m of X coincides with X and is of minimal degree. And in the second case, SIDS n minus m minus 1 of X is either an m plus 1 fold of minimal degree, or m fold of degree n plus 2 minus m, and in this case it coincides necessarily with x.
The Green-Kaplan theorem, we have shown x is projectively normal because he used a section minor when x is embedded in PM.
That it's projectively normal? No, I don't think. Linearly normal should be enough.
Maybe he used the section mean.
Yeah, but it doesn't matter because for KP1s they are the same.
Sectioning and homogeneous.
Yeah, but it doesn't make any difference. So if whether we work with S of x
Yes.
or with the integral closure R of x, say, this is the section ring.
Yes.
The KP1s are the same. And why is that? Because how do we compute KP1 of xx? So this is wedge P of V, tensor V. This is S1 of x. How do we compute this one? Wedge P of V, tensor R1 of x is V again. It comes from wedge P plus 1 of V, wedge P plus 1 of V. And then here there is a difference. Wedge P of P minus 1 V tensor S2 V, S2 X, and this is embedded in wedge P minus 1 of V tensor H naught O of 2. But the kernel is the same, and the image is the same, so KP1s are the same. So it doesn't matter with which one we work.
Yes, so it doesn't matter. The sectioning or homogeneous coordinate ring.
Yeah, we can take either one because we look at the linear strand.
Just looking for linear strand.
Yes, it's always the Ccg varieties are defined only for the linear strand. We don't know how to define in general. So that would be also an interesting question, how to associate varieties to classes in KPQ in general. Probably replacing the homogeneous coordinate ring by the section ring.
It's totally different one.
Yeah, it's totally different. Yeah, because here the difference is that here we only deal with quadrics. So we start with quadrics and we get quadrics at the end. Whereas if we look at KPQ, we might get a mess, cubics and so on. So it could be a mess. So that's why we don't know how to construct, or whether it's possible to construct. Okay. And yeah, one consequence of this theorem is for curves. I think I can, or should I keep? Maybe I can keep a little the definition on the blackboard. So one consequence is the following, is that if x is a curve, a line bundle on x of degree 2g plus 2, genus at least 6, h naught of L is r plus 1, and k r minus 2, 1, xl is different from 0, then x is hyperelliptic. And the reason is the following. So we are in the second situation of Green's KP1 theorem. So X lies on a surface of minimal degree, and because we assumed that the genus is at least 6, cannot be the Veronese surface. So this is a scroll, a two-dimensional scroll. So we have a ruling, and this ruling will intersect the fibers of a ruling will intersect X in a certain number of points. So we get a ruling. And these points cannot be more than 2, because if there were 3 points, then L minus those 3. So this, if there are 3 points on a line, then L will embed with the trisecant line, which means that if we subtract these 3 points, we get a special line bundle. So if the intersection of a fiber with X is more than 3 points, let's call this intersection D. Then L of minus D is a special, and this cannot be because of these degree assumptions. L minus 3 points actually, and minus 3 points is special.
Why is it not Veronese?
Because R is, if we apply Riemann Roch, we get R at least 6,
Yes.
I think. If the numbers are wrong, then we just add increase to 7 or something. But I think 6 is correct. Okay. And that was the starting point of the gonality conjecture, which I'm not going to enter.
Whatever is special, L minus 3 points, if we have 3 points?
Because they don't impose independent conditions on L. If they are on a line, then they don't impose independent conditions. So H1 must be strictly bigger than H1 of L, which is 0. Anyway, this gonality conjecture is solved, I'm very happy to tell you, by Hein and Lazarsfeld. So probably it will be very soon on the web. They have a beautiful proof of...
We have no preprinted yet?
No, not yet, but it will come soon, I guess. And probably with even better results than just with the gonality conjecture. But anyway, the idea is absolutely remarkable, their proof idea. Okay, now let me just mention one refinement of the KP1 theorem, which is a result due to Ibauer. It appeared in a very rare volume, but I gave Sejong a copy of the paper, so everything is in there. If X is a smooth, irreducible curve of genus G, L very ample with the degree at least H0 of L plus 14. R as usual is H0 of L minus 1. Okay, so X is embedded by phi L in PR. And if now we pass to the next one, Kr minus 3, 1 of X is different from 0, then the Ccg variety SIDS R minus 3 of X is one of the following. First, a surface of minimal degree. And since this is a surface, that's R minus 1. A surface of degree R, or a threefold of minimal degree R minus 2. So it's very close to the statement of the KP1 theorem. And as a consequence, there is something similar, corollary, but this time the degree should be as in this corollary. Degree 2G plus 13, I guess, or anyway, slightly bigger. And Kr minus 3, 1 XL different from 0, then X is trigonal or hyperelliptic. The proof idea being the same as in the in this corollary. So
question on KPN theorem. K n minus 1.
yeah, this is for any. Sorry, D.
Second case of the KP1, this former KP1 theorem.
Yeah, this is for curves. There is a small problem when passing from varieties of small dimension to varieties of bigger dimension. The syzygy, taking syzygy variety does not commute with taking hyperplane sections. Does not necessarily commute. So this is a slightly difficult problem, how to control this. Because otherwise we would say, if we have a bigger variety, take a general hyperplane section and we decrease the dimension. But then the syzygy variety, the hyperplane section of the syzygy variety is not necessarily the syzygy variety of the restriction of that class. So one should be a bit careful with. Okay, and first up, now the first open problem.
When is the IMAR solution? Because is in
90, Sejong has a copy of it. 95.
Before 200.
Yes, before 2000, yes. So the first open question, open problem, is generalized. First to Kr minus 4, 1. So that would be the first the first thing to do. Well, E-Bauer only uses projection of syzygies. This is the main thing, plus a very fine analysis of the cases. When you project all the way down to P4 or P5, what is the minimal allowed R here, you have to be and generalization of the strong Castelnuovo lemma, because passing from curves to points is still fine. So beyond projection of syzygies, the other thing he does is an analysis of the case when it's embedded in a very small projective space. So I think this is a feasible problem, but could be technically very involved. So someone told me that when Ebauer worked on this problem, he used to walk around in the department with long sheets of papers, just glued together by using scotch. Okay. So what's the relation with projection of syzygies? The relation is the following. So, well, you know very well the projection of syzygies. But what's interesting is that it has something to do with syzygy varieties. So let me just remind you how to define. So if alpha is an element in Kp plus 1, 1 of x, so again x is non-degenerate and and we consider x to be just for simplicity, the first coordinate points, and we take w inside V, the span of the variables x1 to xn. So we just remove x0, and the projection from Pn to Pn minus 1 induces a projection of syzygies in the following way. So we have a projection map from K P plus 1 Sx V to Kp plus 1, sorry, Kp1 of Sx W, but just we have to be careful. Sx in both is Ss or K of x naught xn divided by Ix. So in both cases we have the homogeneous coordinate ring of x in the original Pn.
Effect is both in both
members, here and here. So we would be tempted to say that whenever we take a projection, so we have x is embedded in Pn, the image is embedded in Pn minus 1, we take a syzygy, we project it, and we get a syzygy for the projected variety. Well, this is not the case. So in general it is not the case. And this is exactly the meaning of the syzygy variety. It takes care of this this pathology. So the question is, when is the projection of some Koszul class for the image of x via Rx. And the answer is the following proposition. So let's call the image Vrx of x to be y. This is in P n minus 1. So we have the following proposition. Prx of alpha is in Kp1 of Sy w, and this is embedded in Kp1 of Sx w with that notation, because here we only have polynomials which do not depend on x0. If and only if x belongs to the Ccg variety of alpha. So in other words, another interpretation of a Ccg variety is that it's the biggest variety, well variety scheme is the biggest variety for which the projection of Ccg would give a Ccg for the projected object.
First, x is not in x. Small x is not large x. So it's outer projection.
So it's outer projection, yes.
Yeah. And how?
So if it's inner projection, then it's automatic.
It's automatic.
Yes, because x belongs to, x is embedded in any Ccg variety.
So x cannot be. Yeah, this one is applicable for inner and outer both.
Yes.
Both
Yeah. So it could be inner projection or outer projection. Yes. Any.
And how define the Kp1 Sx V2 SW?
Well, in the usual way, you just take wedge P W this time. It comes from wedge P plus 1 W, tensor S0 x, this is K, S1 of x, this is V, goes to wedge P minus 1 W, tensor S2 of x. You just, the coefficients are less than the in the original case. So it's a kind of partial. We take just some of the variables. We don't take them all.
That's the reason P plus 1 to P, right?
Yes. Yeah.
So V is.
Let me also write down this this map. So this is induced by. So we have to project from wedge P plus 1 of. So we have to project wedge P plus 1 of V, tensor V, wedge P plus 2 of V, wedge P V, tensor S2 of X. So the projection map is induced by the projection from wedge P plus 1 of V to wedge P of W, which is given by, so wedge P plus 1 of V to wedge P of W is given by, if you take a multi-vector, x I0 IP, this is mapped to 0 if I0 is at least 1, and x1, xi1, xip, if I0 is 0. And this commutes with the Koszul maps. That's why you have an induced map on the welcome. And yeah, because I'm. What time is it? Ah, it's 4:45. Okay. Oh, so I still have time. For the proof sketch, let me just for simplicity assume that P is 1. In general, it's the same. It's just that the argument is a bit more involved. We have to add some terms in a sum, but the idea is exactly the same. So let me put P0 is x is 1, 0, 0, and Pi's are the other coordinate points 1, 0. And well, we can assume that. So we can assume that P1 up to Pn belong to X. So the problem is whether this is X belongs to X or to something bigger. What happens? And we can also assume that X is the syzygy variety of alpha, and we can take then an inner projection to be a genuine inner projection. Okay. Well, in this case, if P0 is in X, so X is cut out by quadrics. So we have those quadrics. Sorry. I was here. So if P is 1 for simplicity, then alpha will be a sum of xi tensor qi with sum of xi qi is 0. So in general, we will have multi-index with similar relations, and we play the same game. So if P naught is in 0, then what happens? If the coordinate points belong to X and the Qi's cut out our variety X, then Qi's will not contain terms of type xi squared. But if P0 is in X, then there is no X not squared in the Qi's.
I complete. You assume P equal to 1 or P equal to 2 for simplicity?
P equals to 1 because I consider the projection to go from P.
P plus 1.
Yeah, P plus 1.
Thank you.
Okay, and we want to prove that. So the projection in this case of alpha will be just Q0. We want to prove that Q0 does not depend on X0. We know so far that there is no, since P0 is in X, there is no X0 squared, but might be different terms containing X0. But if we look at this relation here, we would see that we have a term X0 Q0. So if Q0 depends on X0, then in X0 Q0 we would have a X0 squared times some Xi. And this will have to cancel. But this cannot be because for the other Xi, the Qi does not contain X0 squared. So it's just a closer look at this relation. And in general, for arbitrary P is exactly the same. It's just that this relation is a bit more complicated. So yeah, it's harder to write down than to explain.
Do you think why F not here is not in Qi?
Because
I equal to bigger than 1?
Qi, no, for any I.
Any I.
Because Qi on P0 is 0. And this is the coefficient of x0 squared in Qi.
Yes.
So the coefficient of x0 squared in Qi is 0. So this term, this monomial does not enter in Qi.
I see.
So the other way around. So if Q0 does not depend on x0, we would like to prove that all the Qi's vanish on P0. Well, for Q0 is automatic because it doesn't depend on Q0. But for the others, we have to prove it. So if there is an I such that Qi of P0 is different from 0, then the monomial x0 squared enters Qi. And now we have to look here back again. So in this relation, so we have one degree 3 monomial xi x0 squared. How can we cancel this? Well, just by multiplying with x0. But x0 only multiplies with q0. And q0, that would mean that there is a monomial xi x0 in q0. And this is not possible because q0 does not depend on x0. So this is somehow the game we play. Anyway, this was proved by Ebauer. It was not in this form. So Ebauer proves that if you take an inner projection, then the projection of an element is a syzygy. Projection of a syzygy is a syzygy, but the same argument works to prove this proposition. Okay. And now another idea for classifying these syzygy varieties. Probably now it's time to erase the definition. So there are two possible directions. One is to generalize Green's KP1 and Ebauer using refined techniques, probably new ideas, I don't know, or to try to do something else. And that's what Schreier and his school proposed. And for that I need the definition of a rank of a syzygy. So the rank of a syzygy that was introduced by von Bottmar. So the rank is the following. If we take alpha, an element in wedge P of V tensor V, it's like for syzygy varieties, we don't have for the moment any variety involved. The rank of alpha is the minimal dimension of subspace W such that alpha is in wedge P of W tensor V. So we try to reduce as much as possible these variables here. So we try to eliminate as many variables as possible from the formula giving alpha. Let's make some remarks. So this notion behaves quite well. So the rank is at least P, of course, because otherwise we would get 0 here. The rank only depends on the class. So it's like, again, like for syzygy varieties, wedge P of V tensor V mod out wedge P plus 1 of V. And von Bottmer, using a suggestion of Schreier, introduced the following definition: generic Ccg schemes. So the idea is that, roughly, very roughly, whenever we have a syzygy, so this means a linear relation which gives a syzygy variety, the idea would be to pass to the general situation and some coefficients to see some coefficients as independent variables. So to pass to another ring and see them as independent variables, see what's going on there, and then come back to the original situation. Anyway, let me give you the definition and then I'll explain. So let's suppose W is a subspace of dimension P plus R. So we have we denote by T wedge R of W, direct sum W. That's a bigger vector space. And now wedge R of W, tensor W, is contained in S2 of T, because this decomposes as S2 of the first one plus the tensor product of these ones plus S2 of the second one. And Koszul map from wedge R plus 1 of W, wedge R W tensor W, together with the this inclusion, gives an inclusion wedge R plus 1 W into S2 of T. So S2 of T are quadrics on the space T. So we get a bunch of quadrics on another space bigger than W, and they generate an ideal. So the ideal they generated by wedge R plus 1 of W is called the generic Ccg ideal of W. It only depends on W. And the
P and R.
Sorry?
What's the P dimension of?
This is P plus R. Well, this, yeah. this depends on W and R. This only depends on W and R. This is just a convention. It's P plus R.
What's the dimension of V? V is
The dimension of V was n plus 1. So the dimension of V is fixed. Okay, and the scheme in P dual defined by this ideal is called the generic Ccg scheme, and it's denoted by gen SIDS RW, just to emphasize the two quantities that define this this object. Okay, so we have this pretty complicated object. The question is how is it related to syzygy varieties? Why do we want to look at such things? Well, they are related in the following way, and they are it's quite nice relation. So if we take alpha in wedge P of W tensor V, so in general we assume that alpha has some rank, so the variables can be reduced to a subspace which is some W. So alpha is an element here. Then we had SIDS alpha. We had two objects, SIDS alpha and gen SIDS R of W, and the relation is the following. So alpha defines a map from wedge P W dual to V, can be seen as a linear map. But this is, since the dimension is P plus R, that's why I chose this convention. This is isomorphic to wedge R of V. So there is a map from wedge R of V to wedge R of W to V. So now, together with the inclusion of W in V, we get alpha prime from wedge R W plus W to V. This is a linear map. So let's call gamma the image. We have another. So this was T in our notation. So this will induce a map from S2 of T to S2 of V. Another induced map. Let's call this alpha double prime. And then we have a commutative diagram, which is the following, and this explains the relationship. So wedge R plus 1 of W goes through this, let's call this psi, S2 of T. Then we have alpha double prime to S2 of V. This is isomorphic to wedge P minus 1 W dual. And this is a map which corresponds to delta of alpha. So delta of alpha is an element of wedge P minus 1 W tensor S2 of L, which can be seen as a linear map from here to here. So this diagram commutes. So in particular, SIDS of alpha, so the ideal of SIDS of alpha is generated by the image of this map. So this map will give a bunch of quadrics, which are the quadrics from the beginning, from the definition. And here we have the other quadrics. And this is, this means that, so this diagram here means that, so these quadrics define the generic Ccg scheme, and these quadrics define the other Ccg scheme. So this means that this guy is a cone over, so this is a cone over a subscheme Y in P of gamma dual, which is a plane section of gen SIDS R of W. Yeah, because we had, so gamma in V was the image of the map from T to V.
What is gamma? Gamma
Is the image, let me see, is the image of this this alpha prime. So this is alpha prime. So this is surjective, is the image of alpha prime. So gen SIDS is in P of T dual, the other one is here. And they are related through this diagram. So the bottom line is that if we understand gen SIDS, then we pretty much understand SIDS also. Or at least we have some useful information about. And we will see that gen SIDS is much simpler to classify than SIDS. Let me probably, is it okay if I continue for another 10 minutes or so? So let me give you a toy example, which is due to Schreier. Is in case P equals 2. So in case P equals 2, we have Q1 up to QR plus 2 quadratic forms, and L1 to LR plus 2 linear forms that give a relation. So we have a syzygy. Then W is the span of these linear forms. So we are in the case P equals 2 again. So we are looking at K2, 1. This is the case we analyze. Okay. Then Schreier proves that there is a R plus 2 times R plus 2. This is a general fact. Whenever you are given a bunch of quadratic forms and a bunch of linear forms with the relation, then there is a matrix. So this there is an R plus 2 times R plus 2 skew symmetric matrix of linear forms Aij. So on the diagonal we have 0, such that Qj is the sum of Li Aij. So we have, every time we have a relation, then we have a particular form for this quadrics. And now the Syzygy variety is just the variety defined by these quadrics. So we are looking at V of Q1, QR plus 1, R plus 2. This is the Syzygy variety. And how do we see the generic Syzygy variety in this case? Well, the idea is to see all these Li's and Aij's as independent variables. So this is the passage to the generic situation. So to understand gen-SIDs R of W, we pass to the ring K of L1, LR plus 2, A12, A R plus 1, R plus 2, seen as independent variables. That's why I use the capital notation. So in how many variables we have? R plus 2 plus R plus 2 choose 2. So this is R plus 2 times R plus 3 over 2 variables. And we get the, so the equations here will be, so Qj's will be the sum of Li Aij, and gen-SIDs is given by the vanishing of these Qj's. So this is the difference between Syzygy and so to recover the Syzygy we need to take the necessary relations and go back. Probably it's more even clearer if we see what happens with the twisted cubic again. Or this is a question mark or an exclamation mark. So in this case we can choose one of the two relations. So we had the quadrics Q0, which is x1 x3 minus x2 squared. Q1 is x1 x2 minus x0 x3. Q2 is x0 x2 minus x1 squared. So these are the minors of the matrix to the 2 by 2 minors. And we take the element, so we choose one relation. We take the element x0 times q0 plus x1 times q1 plus x2 times q2. So W in this case is the span of the first three variables, x0, x1, x2, so it's only x3 which is left out. The matrix A from Scher's description is this one, 0, minus x3, x2, minus x1, 0, 0, and then we anti-symmetrize it. And the generic Ccg scheme in this case lies in P5. Where we have coordinates x0, x1, x2. So luckily we don't need to consider new variables because they are already independent. And A10, A20, A21. Okay, and if we make the following change of variables, so this I call y2, this I call minus y1, and this I call y0. Then the generic Ccg scheme is defined by the 2 by 2 minors of the matrix x0, x1, x2, y0, y1, y2. And this is we know what this is. This is the image of the Zegra map, P1 times P2. P1 times P2 in P5. So the generic Ccg scheme is a Segre variety, and the Ccg scheme is the twisted cubic. Well, the twisted cubic is a section of this variety. So this means that the map, the corresponding map, gamma would coincide with V in the former notation. And let me just just to finish, what are the classifying results of von Bottmer? So just I wanted to say that actually Schreier defined the generic Ccg schemes for P equals 2, and then von Bottmer generalized it for any P. That's somehow the development of this notion. Okay, so classification. Is for small r. So r equals 0, the minimal one. The gen SIDS 0 of W is P W dual union with a point. This is seen in P W dual plus C. This is T in this case. R equals 1. Gen SIDS 1 of W is the image of the Segre map, of a Segre map, in the following way. So in this case T dual is W dual plus W dual. This can be seen as W dual tensor K squared. And then we have a map from P W dual times P1, the Segre map, to P T dual. And the generic Ccg scheme is the image of this map. Well, in the first case, we get the Ccg schemes are unions of a hyperplane and the lower dimensional plane. Here we get the Ccg schemes are rational normals cross, and for r equals 2, in this case T dual is W dual plus wedge 2 W dual. Sorry, I exchanged the factors. I just leave it this way. And gen SIDS 2 of W in this case is a Grassmannian union with the plane. And that's basically everything we know about classification. So for r equals 3, it's a complete, it's totally open. So the second open question is for r equals 3. What is the generic Ccg scheme? Okay, and I will stop here. Thank you.